So right here we have a second order linear differential equation. The second derivative of y plus a times the derivative of y plus by equals 0, where a and b are constants. There is a very neat way to solve this, and I will first go through the method and then I will prove the result. So first of all, let's look at the method itself. So the first method is, well, the first case is where the polynomial x squared plus ax plus b equals 0 has two distinct roots. Let's say lambda 1 and lambda 2. Well, of course, lambda 1 and lambda 2 can be complex. They just have to be distinct. Then the solution to this differential equation the solution to 1 is y equals a times e to the power of lambda 1x plus b times e to the power of lambda 2x, where a and b are constants. Well, constants. So a and b can be determined if you have the initial conditions. Let's say you have two values of xy, well, two pairs of values of xy, then you can solve for a and b. So this is the first case, and the second case is where x squared plus ax plus b equals 0 has a repeated root, right? Has a repeated root. Let's say lambda. Then the solution to 1 is y equals ax plus b times e to the power of lambda x. So in the case where this polynomial, which came out of nowhere, has a repeated root lambda, so it's kind of like the case where lambda 1 equals lambda 2, but if we use the same logic, we don't get we don't get ax plus b, we just get a plus b. So it's a bit different. So here we have ax plus b instead of a plus b. So yeah, we have to keep note of that. Next, let's try to prove this. The usual way people usually kind of like prove this statement is they try to prove that, so attempted proof, which it's not complete, by the way. So people might attempt to prove that, the first goal is to prove that y equals e to the lambda 1x works, and then prove that y equals e to the lambda 2x. Well, we're looking at the first case. Then they conclude that y equals a e lambda 1x plus b e lambda 2x works. So most people try to do this because it's simple and it's short. For example, if you look at the first part, why does e to the lambda 1x work? Because dy dx is equal to lambda 1 e to the lambda 1x by the chain rule, and d squared y dx squared is just equals to lambda 1 squared e lambda 1x. So 1 becomes, well, the left hand side of 1 becomes e to the lambda 1x, and then lambda 1 squared plus a lambda 1 plus b equals 0. And why is this 0? Because lambda 1 is the root of the polynomial x squared plus ax plus b, and hence this thing is 0, and multiplied by this exponential, which is also 0. So yeah, and it works the same way for the second part. And hence by linearity, because as you can see, if if y1 works and y2 works, then y1 plus y2 will also work, right? So this thing will absolutely work. But the problem with this proof is that it only finds a set of solutions that work. We never prove that these are all of the solutions we need, right? And also, well, the proof for the second case is similar, but it's still not complete if we do it this way. So let's try to actually prove this theorem and prove that these are all of the solutions. So let's try to prove complete proof. So to do this, let's just assume we have we are in case 1, right? So y prime prime plus ay prime plus by equals 0, and x squared plus ax plus b, which is, by the way, called the auxiliary equation, or the auxiliary polynomial or characteristic polynomial. Let's say it has roots lambda 1 and lambda 2, right? So first of all, well, the motivation is this. The motivation comes from this false proof that we've talked about previously. So we know that y equals e to the lambda 1x works, right? So instead of assuming that's the y we want, we do this. Let y be, let's say, t, or maybe f, right? F times e to the lambda 1x, where f is a function in x. So this is valid, right? Because we can just say, oh, this is equivalent to saying f is y times e to the minus lambda 1x. So it's a perfectly valid substitution, and I claim that this substitution will simplify this equation by a lot, right? So let's say y prime, let's find y prime first. Well, notice that f is not a constant anymore, but a function. So we have to use the chain rule. So if we use the chain rule, we'll get something like this. F prime e to the lambda 1x plus f times the derivative of the second part, right? So that's lambda 1, f e to the lambda 1x. Well, let's simplify this because we know there's a common factor. F prime plus lambda 1f e to the lambda 1x. And then y prime prime would be the derivative of that. So that would be f prime prime plus lambda 1 f prime e to the lambda 1x plus lambda 1 f prime plus lambda 1 f e to the lambda 1x. So let's simplify this, and we get 2 lambda 1 f prime plus lambda 1 squared f e to the lambda 1x. So we have three, well, we have the expressions for these three terms, y prime, and y prime prime. And we substitute back into 1 and see what it simplifies to, right? In fact, recall this factor here. It appears in y prime and y prime prime. So after we substitute it in, we can literally just cancel off that term. So we just have to look at these terms here. So 1 would become, well, the first term is y prime prime. So that gives us f prime prime plus 2 lambda 1 f prime plus lambda 1 squared f. And the second term is ay prime. So that's a times y prime. Y prime, the important bit is this part. And for the last one is by, and so we have b times f. So this is 0. And let's look at some stuff that we can cancel. For example, let's look at the coefficient of f, right? F prime prime plus 2 lambda 1 plus a f prime, and then plus lambda 1 squared plus a lambda 1 plus b f equals 0. And recall that lambda 1 is a root of this characteristic polynomial, and so this thing is 0, right? Okay, now we're just left with these two terms, which is an immense simplification, right? And let's see, one more thing. By the sum of roots, well, theorem, a should be minus lambda 1 minus lambda 2. So 2 lambda 1 plus a, that would be minus, so 2 lambda 1 plus a, that would be lambda 1 minus lambda 2, right? So we can get rid of the term a. So what we get is just f prime prime plus lambda 1 minus lambda 2 f prime equals 0. And let's, well, try to write this as the derivative of f prime plus, or we just write it like this, lambda 2 minus lambda 1 f prime. Okay, and remember that we assume that lambda 1 and lambda 2 are distinct, and hence this thing is non-zero. Now, this is a differential equation which is variable separable, so we can bring f prime here and then take the integral lambda 2 minus lambda 1 dx and take the integral, and this is the natural log of the absolute value of f prime equals, well, lambda 2 minus lambda 1 x plus a constant c. Well, taking the exponential on both sides, we get f prime equals a constant times e to the lambda 2 minus lambda 1 x, where c can be any real number, right? Well, c is a constant. It can be any constant because in this case, if we omit the absolute value, we can allow negative numbers to appear. So this f prime. And how do we get f? We just, well, take the integral again. And if we take the integral, we would have c over lambda 2 minus lambda 1 e to the lambda 2 minus lambda 1 x plus another constant, c2. Well, of course, this is a new constant, so let's rename that into c1. Okay, so what do we have just now? Y was f times e to the lambda 1x. And now we solved for f, c1 e to the lambda 2 minus lambda 1x plus c2 e to the lambda 1x. Now, as you can see, the first term gives us c1 e to the lambda 2x, and the second term is c2 e to the lambda 1x. And finally, that's the proof for the case where lambda 1 and lambda 2 are distinct. So in no way that we omitted any solutions. So here's the complete set of solutions. So for the next case, case 2, where x squared plus ax plus b has a repeated root at lambda, so it's x minus lambda squared. Well, the proof is almost the same, except in the last part here, because in this case, lambda 2 minus lambda 1 is 0 instead of a non-zero number. So I will not repeat the proof. I mean, I will omit the first part of the proof. So we let y equals f times e to the lambda x. Then eventually, using the same methods above, we would get df prime over dx equals 0. So basically, this step over here. So here it will become 0 instead. And if that's 0, then f prime is a constant. The constant, and hence f is c naught x plus c1. And we substitute back inside, we would get ax plus b, where a and b are constants. And here it is. So these are the proofs for the two cases, for lambda and lambda 1, lambda 2 being distinct, and lambda 1, lambda 2 being the same. Well, but this is only for the second order case, right? We can generalize it to, well, the nth order. So here's the nth order version. So it's an nth order linear differential equation. So basically it's yn plus, let's say, an minus 1, yn minus 1 plus dot 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 plus a naught y equals 0, where of course y to the power of brackets n means the nth derivative of y. So the method is completely the same. So first of all, we look at the auxiliary polynomial xn plus an minus 1 xn minus 1 and so on, plus until 0, a0. So if we have n roots, right, the roots are lambda 1, lambda 2, dot dot dot, lambda n. If they were all distinct, it's a very, well, that's most of the cases. If they were all distinct, then y would be just a linear combination of well, e to the lambda x plus c2 lambda 2x plus dot dot plus cn e to the lambda nx. But if some of them are repeated, well, I will just say, for example, let's say lambda 2 is equal to lambda 3 to lambda m, for example, then we basically replace those terms that involve lambda 2 to lambda m. We replace c2 lambda 2x plus dot 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 plus cm e to the lambda mx with c2 e to the lambda 2x plus c3x times e to the lambda 3x, and then c for x squared until we reach the last term, which is cm, and in this case it will be m minus 2, for example. It's just an example. So instead of the linear combinations of e to the lambda x, it becomes, well, we paste another x power k term in front, and of course these are actually the same thing, so you can just say they are lambda or something. I will not prove this general case, but you can prove it by induction if you want. It's completely the same. It's just a very complicated version of the second order version. Or there is a proof given in, well, given in terms of matrix exponentials, which is quite a advanced topic. Maybe I will talk about it next time. But yes, so here is the method and the proof for a linear differential equation.